So let's start the last session of this day with Avishay from Soda Labs talking about his Garbled EVM.
It's not the last session?
It's 3 more talks, right?
Oh, yeah, okay. The last chapter.
Yeah, 3 more talks.
Thank you, Akash. I'm happy to be here, and I'm Avishay from Soda Labs. I'll speak about gcEVM. It's a Garbled EVM. I'll speak about the challenges and architecture, and hopefully after this talk you'll be convinced that Garbled circuits are a good form of MPC, and you will want to use them as well. So what's in this talk? So I'll do one slide on the past versions of privacy on blockchains that we've known so far. Then I'll speak about the challenges of integrating blockchains with privacy solution. And here I'll not focus on a specific privacy solution. I'll pose some questions regarding any privacy solution with any blockchain, and I'll raise some questions that nobody actually scientifically took care of so far. Then I'll review some privacy solutions. Some of them you have already heard about today. I guess you haven't heard about Garbled circuits today, so I'm happy to be the first to talk about this. And finally, I'll build a case for Garbled circuits as a solution for blockchains, and hopefully I'll convince you that this is a very good solution in terms of performance and design for blockchains. And if there is time, I'll show you some examples. So privacy is a wide term. It may mean a lot of things. Definitions can vary a lot. If you see on papers, there are many definitions for privacy. Sometimes they are specific for certain things, and sometimes they are general. But many times they are divided into two other terms, like anonymity and confidentiality, where anonymity is more of the metadata privacy, and confidentiality is more of the data privacy. So if you think, for example, on a WhatsApp application, then anonymity means that you want to hide the persons who speak with each other, the communicating parties, and confidentiality is about the messages themselves that you want to hide from any trusted server. In the blockchain, anonymity is the sender and receiver, for example, and confidentiality is the amounts of the transaction of the funds that you want to transfer. Sometimes it's the amount of the liquidity that you contribute to some AMM or anything else, basically. So the history of privacy for blockchains can get back already to the days of the Bitcoin inception. So the world of blockchains, we can divide it into UTXO-based model and account-based model. So in the UTXO, we have Bitcoin, which has no anonymity and no confidentiality. Then after the Bitcoin inception, there were a lot of projects that tried to solve anonymity and some limited version of confidentiality, like Zcash, Monero, some variants of Mimble-Wimble, and so on. In the account-based, we have Ethereum, which basically inherited the same privacy properties of Bitcoin. So there's no anonymity and no confidentiality. There are many ZK-based protocols to solve anonymity and partial confidentiality on Ethereum, and basically they implement the same techniques that were implemented for Bitcoin, the same techniques basically as Zcash, just on-chain in a contract on Ethereum. And finally, I'll focus more in this talk is about general purpose privacy solutions, like the one that we developed, the gcEVM, what we want from them, and how we build them. So, as I mentioned, I'll focus here on the general purpose privacy solution that gives developer flexible confidentiality. It means that developers can do whatever they want. They can reveal whatever variable, whatever computation results for whoever they want. So they can reveal results to the public, and they can also reveal results to specific users. It's not all or nothing. So what is flexible confidentiality? You can see in this short snippet, this is from the encrypted ERC20 standard that we developed. So there is a mapping that maps addresses to ciphertexts. Those ciphertexts are the ciphertexts that hide the amounts, the balances of the users. Then there is a transfer function, just like you have transfer in ERC20, except here the amount is ciphertext, is encrypted by the message sender. So the function will return some success Boolean variable that will tell us whether the sender of this transfer transaction had enough funds to send this amount. And to check whether the sender has enough funds, we need to do a secure comparison, or secure greater than or equal. The from balance, which is the sender, has more funds than the amount that he wants to send. This is where we actually need to do some operation securely. Except this operation, there are other forms of data encryption that are more classic. So basically, we have data encryption in motion and at rest. These are the two classic types of data encryption that the industry already used for decades. But a new form of privacy is data encryption in use, which is the one that we introduced here in the gcEVM, and there are some other quite new solutions that also introduce them using different techniques. So flexible confidentiality means that the developer can decide whatever it wants to keep in private and what it wants to reveal. So in this specific case, we are fine to reveal on whether the transaction succeeded or not. But we could keep this secret information as well and reveal this only to the sender, for example. So, given that we've established what is flexible confidentiality, and suppose we have some trusted third party that gives us this functionality. It gives us whatever privacy guarantees that we want, and with whatever flexibility that we want. The question is, are we done? Can we easily connect a blockchain with such trusted third party? And the answer is no. It's still very difficult, and there are many questions to answer before we can actually deploy such a solution. I'll only raise some of those questions here, but there are many more, and I will not explain about our specific solutions. There are many possible solutions in this space, and I think not enough scientific work has been done to solve this formally. So, for example, one question is how validator works. So if you know like details of how Go Ethereum or Ethereum validators work, you know that validators, they execute the transactions just as at the same time they do the validation. So they execute transactions to know how much gas they spend, and also to produce some the new state of the blockchain, so that the new state or state root of the blockchain will be in the header of the new block. But if we consider some arguments of transactions that are secret, then validators can no longer execute those transactions, right? Then how can they build a block if they cannot execute those transactions? So there must be a solution for this, of course. There are other questions. For example, should a trusted third party be blockchain aware? Should it run a node of the blockchain and do some operations based on what he ran? Or should it be just completely outsider and just respond to commands from the blockchain nodes. Again, there's no right answer here. There is a concern that the blockchain nodes will somehow collude, and I mean, if we take this trusted third party as a completely external party and just responds to commands from the blockchain, then there is a concern that blockchain nodes will collude and ask the trusted third party to decrypt, for example, decrypt information that should not be decrypted, or to change the value of some information that was not dictated by some transaction in the blockchain. So if you integrate blockchains with any privacy solution, doesn't matter what privacy solution, you need to take care of those problems. Another question is, how long would the trusted third party wait before it decrypts values? Even though there is a decryption operation in the transaction, it may end up in a block that is not final, right? So should it wait until this block is final, or should we speculate and decrypt even though it's not final? This is relevant, obviously, also for threshold decryption, threshold signature as well. And lastly, how to ensure that ciphertext remain in a way that could not be abused by other users and by malicious contracts. So because it's a public blockchain, transactions can be seen by everyone, and transactions contain ciphertext. So if I send a ciphertext inside a transaction, then everybody can see that ciphertext. And if I use an encryption scheme that is malleable, then, for example, if I use an auction contract, someone could use my ciphertext in order to generate another ciphertext that is just encryption of some value +1, and then always win an auction. So we need to take care of all of these things and many other things. I will not answer those questions now, because the focus should be more on the MPC solutions that we have developed. So now let's break it down and do not assume that we have a trusted third party. First, let's see what are the properties that we want from such party before we implement it. So the first thing is flexible confidentiality, as I mentioned before. We want it to be easy for developers to use it and to decide what should be private and what not, so that it will be easy to build applications and to use it. The second thing is to avoid having single points of failures. So there's another slide about it. So for example, this eliminates TE-based solutions, because if you have one TE, then you're risking availability. If you have multiple TEs, then you're posing a lot of single points of failure to your system and risking privacy for the users. Then we want it to be verifiable. This means that even if, I'll speak about MPC solutions. So even if all the nodes of the MPC collude, you still want to not break correctness. It's fine if, it's not fine, but you will live if at some point there is a very strong attacker who managed to corrupt many of the parties in order to break privacy, but you want to make sure it can never steal your funds. So verifiability is very important. And performance should align with the underlying blockchain. So if the blockchain is, for example, it has high throughput, like Solana, then you still want to keep up with the pace of that blockchain. So let's review the high level of the solution alternatives. So we have zero knowledge. You heard a lot about zero knowledge today. I'll not expand too much about it. So the pros is that it's completely trustless. Users can store their information in their phone and never disclose it to anyone except selective disclosure of whatever they want. The cons are that its functionality are limited. You cannot store, you cannot have proofs on shared state that you don't know the value of, right? And it was also shown that for some applications, for example, to prevent MEV on blockchains, zero knowledge will not be sufficient. You need to use other techniques to solve this. I already mentioned TE plus ZK. So TE basically is used for privacy, and ZK for verifiability. This is the way people are exploring how to deploy TEs in blockchain and maintaining verifiability. And the rest of the approaches are based on MPC. So let's review 3 approaches, MPC approaches that we could use in order to bring privacy to blockchains. But before that, let's see what is this MPC? MPC does not mean that the users themselves will participate in an MPC protocol with other users, because we don't expect users or EOAs to be available for the length of the protocol, or even to be available when some contract needs to operate on their values. So the idea is to use MPC as a service and to delegate the inputs to an MPC solution where there is a bunch of nodes that keep the privacy of your inputs. And whenever there is a need to do some computation on your input, they will do it on your behalf. So in this case, for example, there is a user who wants to send some value to the blockchain, and that blockchain uses some MPC solution, which has an underlying assumption of T out of N, secret sharing, for example. That means that there is a threshold assumption that if an attacker attacks more than T of the N nodes that run the MPC, then privacy is broken. But as I mentioned, we still want to have verifiability. So even in this case, correctness is still preserved. Then the user has each user has a secret key, K, and this key is also shared with the MPC nodes. So whenever the user wants to send value to the blockchain, it will first encrypt it. It will first encrypt it using that key, and whenever the MPC needs to do some operation with that value, it will decrypt it inside MPC and then use it. Okay, so the idea is that every user, so whether every user has its own key or not depends on the encryption scheme that you use. If you use public encryption scheme, then there could be one key, but if you use a symmetric encryption key, then you'll need to use a different key for each user. So let's see the secret sharing approach. So in secret sharing, let's say you're given a block. The block is full of transactions, and those transactions contain some ciphertext. And each transaction triggers some smart contract to do some operation on those ciphertext. And overall, you can look at this block as, or you can compile this block as a huge circuit. It could be an arithmetic or Boolean circuit. And then after we have this circuit in our head, we can run a secret sharing based MPC protocol, which basically looks at the layers of the circuit as linear layers and non-linear layers. And whenever there is a linear layer, it means that the parties can do the computation on their own. And for non-linear layers, for example, if you need to compute multiplication, then the parties of the MPC need to communicate, and after they finish the computation of this layer, they can go on to the next layer. So computation using secret sharing based MPC will alternate between linear and non-linear layers until the computation is done. Then FHE based MPC. Actually, in FHE you can do all the computation locally. You don't need to interact in order to compute. So there is some special key called evaluation key, but there is one operation that requires the parties to communicate. So the computation, let's say you got a block, again you represent it as a circuit, and you start doing local computation until there is a point where you need to do decryption. When you need to do decryption, the decryption key is shared among a large or among a set of parties, and every node that do the local computation needs to access that network of threshold decryption network in order to get the decryption result. So the computation is quite similar to the secret sharing based approach, but with much less kind of interaction than secret sharing. But still, there could be scenarios where there might be there could be a sequential decryption operations that need to be run one after the other, and then because there is a lot of round of communication, the latency will be large. Besides that, computation is quite heavy, and ciphertexts are large, which impose some performance issues when integrating, even with performance needs of Ethereum, which is not very performant. There are works that try to implement EthCC on ASICs and FPGAs, but I think we're not there yet. We'll have to see how it goes in the next years. And finally, let's see how it will work with garbled circuits. So what I'll explain now is the naive approach of using garbled circuits for blockchains. So we'll have evaluation nodes as before, and we'll have garbled nodes. This is the new thing here. And the garbled nodes are responsible for two roles. They will do the garbling work, which takes a circuit and create a garbled version of the circuit. And they are responsible also to encode the inputs. So after we know what is the block that we want to compute, we'll take the inputs to the circuits and encode it into something called labels that fit into that big garbled circuit. And the good thing about garbled circuit is that after it's ready, after we have garbled circuit in hand and all the labels, all the encoded input in hand, we can do the entire computation of the block without any interaction. So this is a very attractive property that we want to try and see if we can actually make it more efficient than this. And why we need something more efficient? Because first, as I wrote there, garbled circuits are one time. It means that this garbling procedure need to be repeated many times for every block. It's not like it's not a reusable object. So we must spend some efforts in order to generate it for every block. Besides, even if we are okay with high bandwidth and internet performance are increasing all the time, and data availability sampling are also a problem that is close to be solved. But even if we are okay with spending that communication for generating those garbled circuits, there are still two main issues that we need to solve. The first one is that garbling and evaluation time depend on the number of parties in all the multi-party garbling protocols that we know of, and there are always more papers about it. So, and if the number of parties is large, then it might not be practical or even competitive with EthCC. So we want to solve that. And the second thing is that garbling requires knowing the function that we want to evaluate in advance. So in our case, when we are getting a block to compute, this is the exact point when we know what to compute, and only then we need to start garbling that circuit for that block. but we want to do something else and somehow garble that block before we know what's inside that block. So the question is how we can do this. Let's tackle those two questions in the next slide. So first one is how to remove that dependency in the number of parties. So we deviate from the trivial line of research of multi-party garbling that was started in BMR in the 90s and WRK less than 10 years ago. And we went back to the original YAO idea and separately distributed the garbler and the encoder roles. So now the garbler is some entity that generates YAO garbled circuit, and YAO garbled circuit was meant only for two parties, so it does not depend on the number of parties when you want to evaluate it. So that garbler entity, which is a distributed network, will generate that garbled circuit. And then, and then the encoder, which generates the labels to fit into this garbled circuit, will also be a distributed entity. And therefore, each of those entities now, the network that garbled the function, and the network that encode the inputs to fit to this garbled circuit, they're both operating separately. And then after we have a garbled circuit for the current block, and we also generated the garbled input using the encoder, we can work as before, give it to the evaluator, and then the evaluator will execute the entire block without any communication. The good thing here, when we separate those rows, is that both the garbling phase and the encoding phase are independent of the number of parties. Also, the encoding is very fast. The encoding is I'll show you in the next slide. The encoding is the phase that happens when we get a new block. So it's good that it's very light, both in communication and computation. However, we still remain with bad communication, bad communication complexity because of a large constant in the garbling phase. So our next goal would be to use a garbling based MPC that is independent of the block. So we can do all this operation in an offline phase. So already? Well, last slide. Okay, so okay. Okay, so what we will do is to garble only atomic functions rather than entire blocks. And the idea is to take all the opcodes that exist in the virtual machine that we are running on, and to garble each opcode on its own, and to manage an inventory of all those small garbled circuits. And only in real time, when we get the block, we can assemble all those garbled circuits into one big garbled circuit that resembles all the entire block. And we can do this using soldering, and at real time we can continue and compute the entire block without interaction. The huge work in order to generate that garbled circuit can be done completely offline, independent of the block or the number of parties. So this is the best thing we could achieve. And yeah, so let's go to the next. Yeah, I'll finish here. Thank you.
Time for a quick question, if anyone has.
My knowledge is very limited about garbled secrets, but question. Garbled secrets are really good for Boolean arithmetics, right? What is your experience working with EVM? Is this a bottleneck or no, it's okay?
It's not a bottleneck. Garbled circuit can work also with arithmetic computation, first. And second, we can emulate all EVM opcodes into Boolean circuits as well. So we already did it.
So communication is not too heavy?
The large part of the communication is done completely offline. So whenever we get a block, we can jump to its evaluation phase, which is very fast.
Okay. Thank you.